So, section 2.5, we're going to talk about exponential decay, a very specific case called half-life. And so the half-life, all that means is you've got something that is decaying. How long until the initial amount you have results in you having how much? Half of what you started with. Okay, so if you take some kind of Tylenol in your bloodstream, if it has a half-life of 2.5 hours, that means 2.5 hours after you took it, how much is still in your body? This is where this class would say, how much will be in your body? If you took it, if it has a half-life of 2.5 hours, then you take it 2.5 hours, how much is left in your body? 1/2. That's what half-life means, okay? How much time it takes for half of the substance to go away. That's why we call it the half-life. So really all this is if you look at it, if I had a model that looked like this, 1 minus 0.5, what's the decay rate when you look at that? This is decaying by what rate? Well, 0.5, but I call it in percent. That's how many percent? How many percent is 0.5? 50%. Another word for 50% is a fraction called 1/2, okay? So these models really are all a times 0.5 to a power. It's taking a half. That's why we call it half-life, okay? So it's just a very useful thing to determine, and half-life in terms of substances as they decay. Now, we're going to use a very specific formula here for half-life. You don't need to memorize it. It will be on your test, okay? You'll just see that formula. So the three formulas right now, you know that you're going to see exponential growth, that 1 plus r, and exponential decay, 1 minus r, and then you'll see this half-life formula. So what do these things mean? You should be very used to it at this point. The y means what? Yeah, it's the future value, okay? We've been consistent the whole unit with that. A is the what? Initial value. In our models, x always represented what? Time, okay? And the new thing right here is this h. This is called the half-life. The amount it takes for this substance to decay to 1/2 of the initial value, okay? I mean, a basketball tournament is a half-life. You start out with 64 teams in the March tournament. Well, I know it's more, but let's just say on that Thursday, you start out with 64 teams. In 2 days, how many teams do you have left? 32, right? So in 2 days, you have half the amount of teams you started with. 2 more days later, instead of 32 teams, you have, what, 16 teams. So there's a half-life of 2 days on that basketball tournament. Every 2 days of competition, the number of teams is decreased by half, okay? So let's look at an example here. Uranium-235 was the primary isotope in the World War II bombs over Hiroshima and Nagasaki, Japan. Uranium-235 has a half-life of 703.5 million years. The bomb contained 2 pounds of uranium-235. Write an equation that models the decaying uranium-235. Okay, so the formula we're using is our half-life formula. Y is the future value, A is the initial value, 0.5 is just 0.5, X is my time, and H is my half-life. Okay, so I'm just going to have to figure out which of these things go where. Okay, so we're going to model this to figure out how much uranium is left. So I'm going to say the amount of uranium over time. So I'm just going to call it U of T. What's the initial amount? What's the initial amount of uranium? 2 pounds. We started out with 2 pounds when that bomb was dropped, and then it's 0.5 T over, what is the half-life? Yeah. 703.5. And then what are these variables? So T is the time measured in what? Time in what? Not quite years, something that goes in front of the years. Millions of years, okay? So it's the time in millions of years, okay? That's what t is, okay? And then u is just going to be the amount of uranium measured in what? Pounds, okay? So how much uranium is left after 1 million years? What do I substitute for t? T equal 1, okay? So I'll just go into my calculator and figure out what is 2 times 0.5 to the 1 over 703.5. Okay, so all I have to do is substitute t equal to 1. So 2 times 0.5, raise that to the 1 divided by 703.5. Okay, so I don't have to figure out what is 1 over 703.5 and then raise it. I can put everything in just like you see in the formula. 2 times 0.5 raised to the 1 over 703.5, which is what you see there, and that is what, 1.998. So what is that answer? Yeah, so I've got 1.998 pounds left after 1 million years. You can start to see why we're concerned about nuclear weapons, okay? So how much of this 2 pounds we started with has gone away? 0.002 pounds, okay? That's why we're always concerned about nuclear fallout, nuclear accidents, because that stuff stays around practically forever. You and I are not going to be around even when it gets down to this amount in this formula. Okay, so it's just exponential decay, but the decay is called half-life. So inside that parentheses, you see that 0.5 built into the formula. Let's look at another scenario here. So this is oxy, which is a pain medicine. So oxytocin can be administered oxytocin, we'll try this again, can be administered intravenously through your blood or intranasally inhaled through your nose, okay? The initial dosage is 25 milligrams. The half-life of each method is shown below, okay? So if it's taken in the bloodstream, the half-life is 3 minutes. If it's taken in intranasally, the half-life is 2.5 hours. So that means when you take it, where does it last longer when you take it? Yeah, in the nose, it stays in your body longer. So if you're going to get effects. Now, in your blood, it goes a lot quicker. But if someone is abusing this, which method are they going to take? Which one? In the vein. Why? Because they want what? Yeah, you're looking for all the effects up front. So you're looking for something that's a quicker hit. So that's why some of these medicines were meant to be taken orally or, nasally, or sometimes shot up through the arm because, okay, you get a bigger, quicker hit by doing that. So, okay, let's write models that deal with this. So the amount of oxy after S seconds. So we'll just say, what am I going to name this function? We'll just say the amount in terms of seconds. So the amount of oxy that I have based on the number of seconds, okay? That's going to be, what is the initial dosage? 25 milligrams, okay? Because this is half-life, that formula is 0.5, okay? And then I'm going to have some number, and I'll make sure that's a 5, S over, what is the half-life in seconds? So here's the deal. My formula is for seconds. I want something that deals with seconds. The half-life is what, 3 minutes? How many seconds is that? 180 seconds, okay? So I need this formula to be over 180, okay? So this is my formula. The amount that I have left based on how many seconds after I take it is 25 times 0.5 to the, and this is where maybe I shouldn't have used S, but it's an S. And let me make sure this one looks more like a 5. So 0.5 and then to the S over 180. So that tells me how much is left after a certain amount of seconds. Okay. So all you do in this formula, remember our formula was Y equal A 0.5 and then X over H. So H is the half-life. You just want to make sure that all your units line up. So in this case, you know, S is in seconds and A is my amount in how much milligrams. Okay. How much oxy remains after 2 minutes? What do I need to do with the 2 minutes? It's how many seconds? This is 120 seconds. So I need to plug that into my formula. So I'm going to figure out what is 25 times 0.5 raised to the 120 over 180. That will tell me how much oxy remains after 2 minutes. So go to my calculator. 25 times 0.5 raised to the 120 divided by 180. Oops. 120 divided by 180. That's 15.75. So you see 15.75 milligrams. Now, how much did I start out with? 25 milligrams. How long would it be until I get to half? The half-life is what? The half-life is how long here? Now, how long is the half-life? Come on, guys, you can read it in the problem. It's what? 3 minutes. So after 3 minutes, if I started with 25 milligrams, what amount should I have left over? What's half of 25? 12 and a half. So in 3 minutes, I should have had 12 and a half left over. Does it make sense after 2 minutes that I've got more than that? It does, because it hasn't gone away yet. It hasn't dissipated. Okay, so 3 minutes was the half-life. So in 3 minutes, I should have had half my original amount. So in 2 minutes, I had more than that. It hadn't all dissipated at that point. Now let's write a model that deals with it intranasally. We want something that deals with H hours. Okay, so the amount based on hours. What did I start out with? What's the initial amount? 25, okay? And then it's 0.5 raised to the hours over, what is the half-life in hours? Come on, guys, pay attention. This one's not that hard. 2.5. It's written right there. The half-life is 2.5 hours, okay? So here's a formula for the nasal version that says the amount that you have left based on the number of hours is 25.5 and then H over 2.5, which is a half-life. So H is in hours and my amount is in milligrams of oxy that are left. How much oxy is left after 1 hour? What do I do with this? Yeah, H is equal to what? 1, okay? So this is going to be 25 times 0.5 to the 1 over 2.5. So I'll go to my calculator. 25 times 0.5 raised to the 1 divided by 2.5, 18.95. So there's 18.95 milligrams. So 18.95 milligrams left after 1 hour. How long? I'm solving for what? for H, or time. Solve for time. Time is my exponent. In the world of the last quiz, this would be logarithms. In this quiz, it's going to be your calculator and what command? The menu 3-1, nsolve, okay? So in the intravenous model, that's the one over here, how much until I get to 5 milligrams? So what do I do with the 5 milligrams? That's my what? That's my future amount. So I want to say, when does 5 equal 25, and then it was 0.5 to the, what was that model? S over 180. Okay. So I'm solving for this right here, okay? So in order to do that on the calculator, this is where you just do menu 3-1, and you put this equation in there. So if I do menu 3-1, I need to solve 5 equals 25 times 0.5, and then raise that. If you don't like S, you can use T, it doesn't matter. So I'll use S. S divided by 180, and then you have to tell it you're solving that for what? S, okay? So if I do that, I get 417 seconds. So 417.9. So that's 417.9 seconds. So that's how long it takes the oxy to get down to 5 milligrams. And that's basically, how many minutes is that? So if I take that number, take that number and divide it by 60, almost 7 minutes, okay? So about 7 minutes for get down to 5 milligrams. Okay, so guys, there's not a whole lot new here. The formula is new, but the substituting the values is the same. It's just, this is a very specific formula for half-life, for a decay that is 50%. That's what that's saying. And then the other new thing is in this model where instead of raising it to the one variable t, it's like t over the half-life, okay? Let's look at another example. This is a very common example with half-life as well. If you ever hear, like, you know, they found a skeleton and based on carbon dating, they estimate the skeleton was 80,000 years old. There are elements in the skeleton that have to decay, that take a long time to decay. And one of these is carbon-14, okay? The carbon-14 in a skeleton has a half-life of 5,715 years. That means when you die, you're made up of your living being, you have carbon. It takes 5,715 years for half of that carbon-14 to go away, to leave your skeleton. So they can measure how much carbon-14 is in a bone that they find, and then estimate how old that bone was based on how much is left. So write an equation that models the amount of C14 in a skeleton based on the half-life, okay? So I'm going to say that C, well, let's just make that we'll say that C of T, so it's based on time, the amount of carbon that I have left. What is the initial amount that's in a skeleton when you die? This is all glamorous stuff. What does the model say? What's the initial amount? 0.83, that's how much is initially there. And then the half-life formula is always a 0.5. And then I'm going to raise that to the T over, what is the half-life of carbon-14? Yeah, 5715. And now I just need to define these variables. So C, that is the amount of carbon measured in what? Microcuries. You don't have to know what those are. You just write, it tells you, okay, it's 8.83 microcuries. So C is the amount of carbon in microcuries. My unit of time, what am I measuring time in here? Years, okay. So here's my formula. how much C14 would be in a skeleton 1,000 years after death? So the 1,000 gets plugged in for what variable? T, okay? So I just need to figure out what is 0.83 times 0.5 to the 1,000 over 5715, okay? Anyone know that off the top of their head? So 0.83 times 0.5 raised to the 1,000 divided by, was it 5715? 0.735. So it is 0.735, whatever a microcurie is. Okay. So you started out, the skeleton had 0.83. 1,000 years later, it's got 0.735 is the amount in the skeleton. Okay. Next question starts with two words. How old? That means I'm solving for what? Which one? Time. Anything that has to do with how old or when or how long or all of that, that's time. Time is always my what? Exponent. Okay. In this test, you have a new way of solving for the exponent. It's the nsolve command. So somebody was asking in the other class, can't we just nsolve all the time? No, you can only use it when you're solving the exponent. In this case, if I know all the numbers, there's nothing to be solved. You plug things in. You only use that solve command when you need to solve for the exponent. Okay? So, what is the equation I need to solve? What do I do with this number? What does this mean? This is the what? Yeah, that's the future value. I found a bone and it had 0.072 microcuries in it, and I'm trying to ask how old it is. So I found something that had 0.072, and I just go back to that same formula that I had. What was it? 0.83 times 0.5 to the t over, what was it, 5715? So just go back to that same formula. And then how do I solve this guy? This is where the class would interact with the teacher. How do I solve this? Menu 3-1. I'm going to solve this, okay? So what do I put in here? Just that equation. 0.072 equals 0.83 times 0.5 raised to the t divided by 5715, and then what? Comma t, okay? It's not that difficult. It's just, I mean, the calculator is doing all the hard work here, okay? So solve this equation and you get 20,157. So t is 20157. In the context of my problem, what does that mean? Yeah, this skeleton is how old? So this skeleton is 20,157 years old. Okay? So again, all we did today was this new formula for half-life. Just keep in mind that half-life is just a very specialized exponential decay. So it's always decaying by 0.5. That's why we've got the 0.5 in the middle here. You should be able to read one of these word problems, write out the model, and then you can evaluate by plugging in values or using the nsolve command.